Giant students, I hope you all are keeping well and staying fit. So today, in today's session, we will discuss about the combination of resistances. Now students, you are aware the resistors offering some sort of resistances in any given circuit can be combined either in series or in parallel. So in this session, we will be discussing the combination of resistances when they are connected in series and then when it is connected in parallel. We will consider the case of 3 resistors and then the result can be generalized to n resistors connected in series or parallel, right? So let's begin with the first case, that is when the resistors are connected in series. So let's start with the first one. So we will discuss the series combination. Series combination of resistors. So as you are aware, students, 2 or more resistors are said to be connected in series only when the rate of flow of charge, which is the current flowing across each of the resistor, is same or is constant. And that is possible only when the resistors are connected end to end. End to end means like this, they are connected like this, end to end. These are the 3 resistors and they are connected in this particular manner, they are connected end to end. So whatever current is flowing through the first resistor, the same current would be flowing through the second resistor, the same current must be flowing through the third resistor as well. So that's the mandatory condition for the resistor to be connected in parallel. So again I repeat, 2 or more resistors are said to be connected in series only when the current flowing across each of the 3 resistors is constant, right? So let us consider 3 resistors having resistances of R1, R2 and R3 like this. These are the 3 resistors having resistances of R1, R2 and R3, and they are connected across any source. Combination cell, as you are aware, it's a battery and it provides a potential difference of, say, V between the points A and B. The conventional current is always from positive terminal to the negative terminal. So the current would be like this. Again I repeat, when the resistors are connected in series, then the current flowing across each of the resistor connected in series must be constant, right? Let us consider this to be point C, let us consider this to be point D. Also let us assume when the current flows through this part of the wire offering resistance R1, there will be some potential drop, and as per Ohm's law, potential drop or potential difference is I into R. So let the potential difference between the points A and C is V1. Let the potential difference between C and D is V2. And let the potential difference between D and B is V3. Right? Now obviously point A is at higher potential than point C. That is the reason why current is flowing from higher potential to lower potential. Between point C and D, C must be at higher potential as compared to point D. And between D and B, D must be at higher potential as compared to point B. Current always flows from higher potential to lower potential. I am talking about conventional current, the direction of which is as shown in the figure. Right, students? Okay. This can be redrawn into an equivalent circuit like this. This is suppose RS. RS is the equivalent of all the 3 resistors which are connected in series. This is point A and this is point B, right? And this is the same source. This is the same source providing a potential difference of V. So here the potential difference is V. And what's the current flowing? What's the net current flowing through the circuit? It is I. This is simply the equivalent circuit, right? So what we intend to do is, we need to determine a relationship between RS and R1, R2 and R3, right? So we need to determine the equivalent resistance in the series grouping of resistances. For that, let's make use of Ohm's law. First and foremost, the potential difference between the points A and C. Look, VA minus VC. I told you earlier, current is flowing from A to C. So the potential at point A must be higher than potential at point C. So the potential difference between the points A and C is considered to be V1, which as per Ohm's law is current, which is I, and the resistance provided by this section of the conductor, which is R1. Put this as equation number 1. Similarly, potential difference between points C and D, it will be written in this particular manner. It is V2 and it is equal to I multiplied by the resistance offered by the conductor between points C and D, which is R2. And between D and B, the potential difference would be VD minus VB. It is equal to V3, which is equal to I into R3. Put this as equation number 3. Also, students, if you consider points A and B, then potential difference between the points A and B would be VA minus VB is equal to I multiplied by the equivalent resistance between these 2 points A and B, which is RS, which is the equivalent resistance, right? So put this as equation number 4. Now what we will do is, adding 1, 2 and 3, we will get a very important result. So what we will do is, adding first, second and third, we get, look, when we add these 3, what do we get? Minus VC plus VC will get cancelled, minus VD plus VD will get cancelled. So on left hand side we will be left with only VA minus VB, right? VA minus VB, and that is equivalent to V1 plus V2 plus V3, right? And this in turn would be equal to, I can be taken as common, so it can be written as R1 plus R2 plus R3, right students? Simply add these 3 equations. In the extreme left, these terms will get cancelled, we will be left with VA minus VB, and over here V1 plus V2 plus V3, and in the extreme right, I can be taken as common, and in the bracket it will be R1 plus R2 plus R3, right? And now make use of equation number 4. From equation 4, VA minus VB, it can be written as IRS. It is equal to net potential difference V, and which is equal to IRS. So IRS is equal to I R1 plus R2 plus R3. Since some finite current must be flowing through the circuit, therefore RS is equal to R1 plus R2 plus R3. So students, this is the formula for finding the equivalent resistance when the resistors are connected in series. So what we obtain is, if 2 or more resistors are connected in series, then the resultant of the equivalent series combination is given by the sum of the resistances of the individual resistors. This is known as law of combination of resistances in series, right? We can extend this result for n resistors as well. So therefore, for n resistors connected in series, what we get is, we can write it like this: R series can be written as summation I equals to 1 to n Ri. So this result can be generalized for n resistors connected in series as well. So as I have told you, this mathematical result is known as the law of series combination of resistances, which states that when 2 or more resistors are connected in series, then the equivalent resistance is numerically equal to the sum of the resistances of the individual resistors. So this is known as law of series combination of resistances. Now we need to discuss some very important points which are applicable in the series grouping. So let's discuss those points first. Okay, let's talk about the first point. Let's recapitulate this entire topic. So first point is, in series, students please remember, in series grouping, the rate of flow of charge, which is the current flowing across each of the resistor, must be constant. So current flowing across each of the resistor must be constant. This is the first point. Second, now look, from Ohm's law we are aware V is equal to IR. Therefore, since I is constant, therefore V is proportional to R. So what it suggests is the higher the value of resistance, the more will be the potential difference across that resistor. I'll give you an example. Suppose this is 1 ohm, this is 2 ohm, and let us consider this to be 3 ohm. Obviously, R3 is greater than the other two resistors, right? So, a constant current will flow through each of these three resistors, but the potential difference, that is V3 across R3, would be maximum, while the potential difference across the resistor having minimum value of resistance will be minimum. So, higher the value of resistance, greater will be the potential difference across that resistor, and vice versa. Clear, students? This is valid only in the series case. Third, now current is constant, right? So, if you are having different values of resistances, then the potential difference across different resistances will be different. If the value of R is different, then potential difference will be also different. So, potential difference or potential drop across resistors having different value of resistances, is different. So basically, the most important point is in the series grouping, the current is constant, while potential difference across resistors having different values of resistances would be different. I is constant, but V, capital V, which is the potential difference across different resistors, would be different, right? Fourth point. Now look, students, what would be the equivalent resistance in this case? Series grouping, 1 ohm, 2 ohm, 3 ohm. So it will give us 1 plus 2 plus 3, that is 6 ohm. 6 ohm is greater than the maximum value of the given resistance. So basically what I mean to say is that series grouping of resistors is done when we require much higher value of resistance in a circuit, right? Another conclusion can be made. In the series grouping of resistors, the equivalent resistance is always greater than the maximum resistance of the given value of resistances. So over here, 1, 2, 3, this is the maximum value of given resistance. So the equivalent resistance will be greater than 3, which is 6 ohm in this particular case, right? So again, let me repeat this. In the series grouping, current flowing across each of the resistors should remain constant. The potential difference across different resistors having different values of resistance would be different. Since current is constant, therefore, greater or higher the value of resistance, more will be the potential difference across that particular resistor. And smaller the value of resistance, lesser will be the potential difference across that resistor. And last step, in the series grouping, the equivalent resistance is greater than the maximum of the given value of resistance in the network. Right, students? So, after completing this topic of series combination, let's concentrate on the parallel grouping of resistors. Right? In parallel, the conditions will simply get changed. Parallel means two or more resistors are said to be connected in parallel only when the ends of the resistors must be connected between the same two common points. So what it does is, the potential difference across each of the resistor would be constant, would be same as that of the PD, potential difference applied between points A and B, right? So that's the eventual condition for the resistors to be connected in parallel. So, second is, let's start the parallel grouping of resistances. So, as was in the previous case, let's consider three resistors R1, R2, R3 having resistances R1, R2, R3 and they are connected in parallel. In parallel, just now I have told you, all the three resistors, their ends must be connected between the same two common points. Look, these are the three resistors which are connected across. So they are connected between the same 2 points A and B. This resistor R1, its one end is connected to point A, the other end is connected to point B. This resistor of resistance R2, one end is connected to point A, the other end is connected to point B. This resistor of resistance R3, one end is connected to point A, the other end is connected to point B. So, whatever voltage is applied or whatever potential difference is applied across the points A and B, suppose V, it will be same across all the three resistors. So, here also the potential difference would be V, here also the potential difference would be V, and here also the potential difference would be V. So again, students, I repeat, 2 or more resistors are said to be connected in parallel if the potential difference across each of the resistor is same as that of the applied voltage when we consider 2 given points. Right? So this is the mandatory condition. Now what to do is, current, it always flows from higher potential to lower potential. This point will act as a junction. Here the current is entering, the net current entering is I, and there is another junction, here the current is leaving out this particular circuit. So again the current must be leaving out and its magnitude must be same as that of the current which was entering this circuit, right? We are aware of conservation of charge. Throughout the circuit, at no point charge can get accumulated, right? So it is the continuous flow of charge that constitutes electric current. So at this juncture, which is known as the junction, the current will get divided across these 3 branches. So suppose the current flowing through this branch is I1, suppose the current flowing through the central branch is I2, and the current flowing through this branch is I3. So these 3 currents will again add up and the resultant current would be I. So point here I would like to mention is that in the parallel grouping of resistors, the potential difference across each of the resistors would be constant and the current flowing across different resistors having different values of resistances would be different. Now, suppose the equivalent circuit is this one, R parallel, and this is point A and this one is point B. Net current flowing is I. And the potential difference applied across the points A and B is V. This is the potential difference applied across the points A and B. This is the equivalent diagram. So students, what we intend to do is, we need to find out the relationship between R parallel, R1, R2 and R3. Right? So let's start the article. So here we will begin with the fact that the current entering a junction must be equal to the sum of the currents leaving it. So therefore, since charge is constant, therefore current must also be constant. In a circuit at no point the charge can get accumulated. Therefore, the sum of the current entering a junction must be equal to the sum of the current leaving it. Thus, net current flowing through the circuit is I, it should be given by I1 plus I2 plus I3. Am I clear, students? This follows from the conservation of charge. And we'll discuss a rule in the later section that's known as the junction rule, which states that the sum of the current entering a junction, this is a junction. At this junction, what is the current entering this? That is I. And the sum of the current entering a junction must be equal to the sum of the currents leaving that junction. So the currents leaving this junction is I1, I2 and I3. So I current is entering and I1, I2, I3 currents are leaving from that particular junction. So applying this rule, which is known as junction rule, net current I, which is enters, must be given by the sum of the currents leaving that particular junction, which is I1 plus I2 plus I3. So this is as per junction rule, which just now I have stated. Sum of the currents entering a particular junction must be equal to the sum of the currents leaving that junction, right? Now look, we are aware of Ohm's law, isn't it? Ohm's law is V is equal to IR. So this is the basic formula in current electricity. So I over here, it can be written as potential difference between the points A and B is V. And what is the equivalent resistance between the points A and B? It is R parallel. We can write it like this. I1, consider this branch. The potential difference across this is V and the resistance is R1. So it is V by R1. V equals to IR, therefore current is potential difference divided by resistance. So we are making use of this particular formula, right? Similarly, I2, it will be given by V by R2, and I3, the potential difference across the third resistor is again V, same as that of the applied voltage, and the current flowing through it is I3 and resistance is R3. So I3 would be given by V by R3. Here again, it's a reminder that in parallel grouping, the potential difference across each of the resistor is constant. So therefore, it can be rewritten as 1 by R parallel is equal to 1 by R1 plus 1 by R2 plus 1 by R3. Right, students? So for n resistors connected in parallel, we can generalize this result. So it may be written as summation I equals to 1 to n 1 by Ri. So you can write the result in this manner as well, right? So students, this result is known as the law of parallel combination of resistances, which states that if two or more resistors are connected in parallel, then the reciprocal of the equivalent parallel resistance, the reciprocal of the equivalent resistance of the parallel combination is given by the sum of the reciprocals of the resistances of the individual resistors. I repeat, students, in case the resistors are connected in parallel, then the reciprocal of the equivalent resistance of the parallel grouping is numerically equal to the sum of the reciprocals of the resistances of the individual resistors. So this is the statement of law of parallel grouping of resistances, right? So let's discuss some very, very important points which are applicable in the parallel grouping of resistors. So first and foremost point is V is constant. Potential difference across each of the resistor connected in parallel is always constant. So that's the key point. Second, current flowing across different resistors having different values of resistance is different. I across different values of R are different. It's simply the opposite case as that of the series grouping. In series grouping, current is constant, potential difference is different across different resistors. In parallel grouping, potential difference is constant while the current flowing across different branches offering different resistances is different, right? Third, we are aware V equals to IR, right? Since V is constant, therefore IR is equal to constant, or I is inversely proportional to the resistance. Let's try to interpret this particular statement. So, higher the value of resistance, smaller will be the current flowing through that particular branch. Clear? And lesser the resistance offered by a device, more will be the current flowing through it. So basically, if we take the example of like 6 ohm, this is 3 ohm, and let us consider this to be 2 ohm. All the three are connected in parallel, right? So this resistor is having least value of resistance. So the current flowing through this would be maximum. Suppose it is I1, it is I2 and it is I3. So the resistor offering least value of resistance, the current flowing through that would be maximum. So it will be I3 would be maximum while I1 would be minimum. So inversely proportional to the resistance offered. Current flowing is inversely proportional to the resistance offered in that particular branch. The greater the resistance offered, the lesser will be the current flowing through it and vice versa. Right? So this is very important. Fourth one. Students, in series, what I have told you is, whenever a set of capacitors are given, a set of resistors are given, and if you want to have maximum value of resistance, then what is preferable? We will tend to connect all those resistors in series. And in case a very small value of resistance is required, then we tend to connect all those given resistors in parallel. What I mean to say is that in the series grouping, the net resistance of the combination tends to increase, while in parallel grouping, the net equivalent resistance tends to decrease. The equivalent resistance in the parallel grouping is less than the minimum of the given value of resistance. So here between 6, 3 and 2, 2 is the minimum value. So here R parallel for this equivalent circuit would be less than 2 ohm. Understood, students? Let us solve it. So 1 by R parallel, it will be equal to 1 by 6 plus 1 by 3 plus 1 by 2. So 6 can be taken as LCM, so 1 plus 2 plus 3. So what do we get? 6 by 6, that is 1. So therefore, in the last step, don't forget to take the reciprocal. So it will be equal to 1, which is less than that of 2 ohm. Clear, students? And these calculations can be done verbally as well without doing any sort of written calculations, right? For example, out of these three resistors, first you can deal with these two, 6, 3. They are connected in parallel, so their equivalent would be 6 into 3 divided by 6 plus 3. Okay, I'll illustrate it in a detailed manner. What we intend to do is to just simplify the calculations while doing numericals. For example, students, look, these are the two resistors connected in parallel. So what is the equivalent formula between these 2 points? It will be given by this formula. Just now we have derived, isn't it? So on taking LCM and in the last step taking reciprocal, what will be left with is R1 R2 divided by R1 plus R2. This formula is recommended, right? So just remember this formula and we can do it verbally only. There is no need to do any written calculation part. Now always remember, if R1 is equal to R2 is equal to R say, then substitute the value over here. So what do you get? R square divided by R plus R is 2R. So that will give us R by 2. So what I mean to say is that if the two resistors which are connected in parallel have same value of resistance, then their equivalent parallel resistance will be equal to half of the given value. It will be half of the given value. For example, suppose this is 10 ohm, this is also 10 ohm. So their equivalent resistance would be how much? Half of this, that is 5 ohm. Right? Suppose 7.5 and 7.5 ohm. These two are connected in parallel. So what will be their equivalent parallel combination resistance? That will be 7.5 divided by 2. It will be 3.75. 6 ohm, 6 ohm. They are connected in parallel. What will be their equivalent resistance? 3 ohm. 12 ohm, 12 ohm. They are connected in parallel. So what will be their equivalent parallel resultant resistance? It will be 12 by 2, that is 6 ohm. Clear, students? So let's try some other questions. Just to speed up the calculations, these are some important tricks which you need to use while doing numericals based on the combination of resistances. Suppose this is 6 ohm and this is 3 ohm. They are connected in parallel, isn't it? What will be their result? 6 into 3 divided by 6 plus 3. It will be 18 by 9, that is 2 ohm.